You know how your phone's GPS stays so incredibly smooth even when the signal's a bit shaky? Or how a spacecraft can nail a landing millions of miles away? Well, the secret sauce behind that is a really elegant algorithm called the Kalman filter. Today, we're going to decode the 5 key equations that make it all work, and you'll see there's a simple genius hiding inside all that math.
So this is the big question, right? This is the fundamental problem the common filter was designed to solve. I mean, think about it. Every measurement we take from the real world is a little bit imperfect. GPS signals have jitter. Camera sensors have noise. So how do you get a crystal clear, accurate picture of what's happening from a constant stream of noisy, unreliable data? Well, that's the magic we're about to unpack. All right, here's how we're going to tackle this. First, we'll look at the super simple repeating cycle that's at the heart of the whole thing. Then, we'll break down the equations for predicting the future, and right after that, we'll cover the equations for updating that prediction with fresh data. And finally, we'll see it all come together in a real-world example. Simple as that.
You know, the real elegance of the Kalman filter isn't how complicated it is, but actually how beautifully simple it is. The whole thing just runs on this continuous, 2-stage loop that lets it constantly learn and get better at understanding what's going on.
And this is it. This is the loop. At every single moment, the filter does just 2 things. First, it predicts where it thinks the system is going next, based on its own internal model. Then, it grabs a real-world measurement and uses it to update or correct that prediction. Predict, update. Predict, update. That's the entire rhythm of the Kalman filter.
So let's dive into that first step, prediction. This is where the filter uses what it knows about a system to make an educated guess about the future. And to make this really tangible, let's imagine our filter is trying to track the position of a self-driving car on a highway. This step has 2 key equations.
This is our first equation, and its job is actually pretty straightforward. Predict the car's new state, so its position and its velocity. It's basically saying, okay, let's take our last known position, apply some basic physics, add in any new steering or acceleration, and that'll give us our new best guess.
So let's break that down with our car example. The first term is our last known state, like where our car was 1 second ago. We multiply that by A, which is just a fancy term for how we expect the car to move based on physics. You know, position equals old position plus velocity times time. Simple stuff. Then we add B, U, T, which accounts for anything new the driver or the AI is doing, like hitting the gas. Put it all together, and we've got our new predicted position. But look, a prediction is pretty useless if you don't know how confident you are in it, right? That's where the second equation comes in. This one estimates the uncertainty, or the error, in our new prediction. It's the filter's way of being humble and saying, hey, here's my guess, and here's how much you should probably trust it. So our new uncertainty comes from 2 places. First, we just carry over the uncertainty from our last estimate, but then we add something called process noise, which is Q. This is basically the uncertainty that comes from the messy real world that our simple physics model can't predict. Think about our self-driving car. Our model knows about velocity, but it has no idea about a sudden gust of wind or a little bump in the road. Q accounts for all that real-world chaos, which means our uncertainty grows a little bit with every new prediction. Okay, so we've made our prediction, and we know how uncertain it is. Now comes the most critical part of the whole cycle, the reality check. We're going to take a new measurement from a sensor, like a GPS reading, and use it to correct our guess. And the absolute heart of this entire update step is a value called the Kalman gain. The best way to think of it is as a trust dial. It's a number the filter calculates on the fly that intelligently decides how much to believe the new sensor reading versus how much to just stick with its own prediction. This right here, this is where the magic happens. Now, I know what you're thinking. That equation looks a little intense. I get it. But just remember its job. All this math is just to compute that one single crucial trust value. It's just weighing the uncertainty of our prediction against your uncertainty of our new measurement to find that perfect balance. Now, the most important variable to look at here is R, the measurement noise. This is just a number that represents how much we trust our sensor. For our car's GPS, is the signal crystal clear, or is it a foggy day with a really weak signal? A foggy day means a high R. H is just a simple translator that connects our internal state to that measurement. So if our state includes position and velocity, but the GPS only measures position, H tells the filter to only compare the position parts. And this is where it all clicks. If our GPS is super reliable, meaning it has low noise, a small R value, the Kalman gain will be high. And the filter will basically say, okay, I'm listening to the sensor. But if our sensor is noisy and unreliable with a high R value, the Kalman gain will be low, and the filter will wisely say, you know what, I'm going to trust my own prediction more this time.
Okay, so let's bring this to life with our traffic light example. Imagine our filter has done its prediction step. Using its internal model of traffic flow, it makes its best guess. There are 18 cars waiting at the light. But at that exact same moment, a new measurement comes in from a camera pointed at the intersection. The camera's image processing counts 20 cars. So now we have a conflict, right? Our model predicted 18, but reality says 20. How do we resolve this? Well, we turn to our next equation. We use equation number 4. This is where we calculate our final corrected best guess. It starts with our initial prediction, the 18 cars, and then it adds a correction term. And that correction is controlled by the Kalman gain, K sub T, our trust dial. Let's look at that term in the parentheses. That's called the innovation, or my favorite way to think of it, the surprise. Our measurement, ZT, was 20 cars. Our prediction was 18. So the surprise is the difference, 2 cars. This is the new information. We then multiply the surprise of 2 cars by our Kalman gain to decide just how much to nudge our original estimate of 18. If we trust the camera a lot, we might nudge it almost all the way to 20. If we don't, we might only nudge it to 18.5. All right, last equation, I promise. Now that we've mixed in some new real-world information from that camera, our estimate is better. And because it's better, it must be less uncertain. This equation's only job is to update our uncertainty value to show that new, higher confidence.
Think of our uncertainty as a bubble around our estimate. In the prediction step, that bubble got a little bit bigger because of that real-world messiness. Well, this final step uses the Kalman gain to shrink that bubble back down. After every valid measurement, our knowledge gets better, our uncertainty bubble gets smaller, and our estimate gets more and more precise. That's the learning process in action.
So let's zoom back out and see how this entire predict and update dance actually works in our traffic management system. In this scenario, the prediction step uses a traffic model to guess how many cars are on a road. The update step then takes readings from real sensors, like cameras or those loops in the pavement, and uses the Kalman gain to intelligently merge that real data with the prediction. The end result is a smooth, accurate, real-time picture of traffic conditions, which is absolutely essential for making smart decisions about when to change the lights. And this quote from the source material really drives home why this is so important. A system that only acts on noisy sensor data or an imperfect model would be making mistakes all the time. The Kalman filter is that crucial correction mechanism that turns faulty information into reliable intelligence. And that's the beauty of it. This two-step dance of predicting and correcting, it isn't just for traffic. It's in your phone's GPS, it's in navigating spacecraft, it's used in economic forecasting. It is a fundamental pattern for making sense of a noisy, messy world. So the only question is, where are you going to see it next?